This video is on electron configurations. I'll get into Bohr a little bit and a little bit of background information, but I'm not going to be really heavy about this because in chemistry what's most important is the electron configurations and how that determines the properties of the elements and how they're going to bond. And essentially, and then you just need to know how to memorize electron configurations, okay, and understand how that affects the periodic properties of the elements. So I'm going to brush through the physics really fast. Not to mention, I'm not really a big expert on the physics as well. Here we go. The basics. Bohr worked with hydrogen, okay? Why did Bohr work with hydrogen? For one particular reason, because it has one electron. And he studied the emission spectra of the hydrogen atom. And what you basically do is you have a lamp, and you've all seen this, where you basically run electricity through it, and the energy associated with that electricity is of the right level that allows electrons within the hydrogen atom to jump up and down between energy levels. And the critical idea is that electrons cannot absorb just any old amount of energy. They have to absorb specific quanta. So an electron can jump from the first energy level up to the second. It can't jump in between. An electron can jump from the first energy level up to the third. It can't jump in between. And so it absorbs that amount of energy, right? And then it can jump back down. And when it does that, it releases a very specific amount of energy, okay, which corresponds to a very specific frequency, which corresponds to a very specific wavelength. Now, some jumps have more energy than others, right? And you should know here, this diagram here shows the relative differences in energy of the different n, which is the different principal energy levels. So if you jump from, let's say, if you jump from the third energy level down to the second energy level, right? So this is from the third to the second right here, right? That jump does not have a lot of energy associated with it. So when you make that jump, what you end up getting is you end up getting red light. Now, what's important about red light? In the Roy G. Biv scenario, red light has the longest, okay, wavelength, which means of the visible light, it has the lowest amount of energy. Right? If you jump from the fourth energy level down to the second, okay, there's a bigger difference in energy, so you end up with green light. If you jump from the fifth energy level down to the second, you get blue light, which in the visible spectrum has the shortest wavelength. Be careful, the shortest wavelength in the visible spectrum, which means it has the highest energy, except for violet, obviously, which is even shorter wavelength and higher energy. But the shortest visible light we're seeing here in the diagram, I guess that's what I'm referring to. Now, what if you jump all the way from the fifth down to the first? Well, that's where you get UV being given off. Okay, so you can get non-visible light given off as well, particularly when you make larger jumps. And you want to note, there's a big difference in energy between the second and the first energy level. And that same amount of energy would have to be absorbed. So a hydrogen atom, if it were to absorb red light, that red light of a specific wavelength would cause an electron, let's say, to jump from the second up to the third. If it absorbed green light, it could cause an electron to go from the second up to the fourth. That's all you really need to know about the background here. If you absorb energy, you move away from the nucleus. If you release energy, the electrons move towards the nucleus. And the only other thing I'd like you to know is the reason why this is all done with hydrogen is because hydrogen only has one electron. When you start dealing with atoms which have many electrons, because of the interactions between the electrons, the math became very complicated, and Bohr really couldn't handle that. Now, I don't want to get into any heavy-duty physics, but a couple of factoids you want to know is that electrons do have a specific wavelength, okay? They are seen as what they call standing waves in things called orbitals, and by means, right? And so they'll sometimes use the term wave function, but we're not going to do anything with those functions. So wave functions are used to describe the orbitals the electrons are in, but we're not going to do any of that math, so I'm not going to bother with it, all right? But they do, when the electrons are in these energy levels or these orbitals, they do have a specific amount of energy, and they do have a specific, they are actually, do have a specific frequency wavelength when they're in those specific energy levels. But let's move on from this and get into what we really need to know, which is electron configurations. Now, the fundamental idea is when an atom is not excited or in ground state, the electrons tend to go into the first energy level first. Now, there are what are called energy levels. That's okay. There are what are called sublevels, and then there are what are called orbitals. All right. And so I think the best way to do this, and this is review. I know you've seen this before, But in this case, you're going to have to memorize the order in which these guys are filled. But there's a trick with the periodic table that we'll get to. So for now, let's make sure we can do electron configuration. Now what this shows you is down here, this is the lowest energy, and this is the highest energy. And so if you have an atom like sodium with only 11 electrons, you're going to fill in the lower energy levels, sublevels, and orbitals first. A couple of really important things to notice here, okay? There are 4 types of sublevels. There are S sublevels, there are P ones, there are D ones, there are F ones. They have different shapes and sizes and have different numbers of orbitals within them, okay? So an S sublevel has exactly 1 orbital, and an orbital can only hold 2 electrons. So an S sublevel can only hold 2 electrons, right? And that's that one circle there. So that one circle there can hold 2 electrons, okay? A P sublevel, okay, can have 3 orbitals, and since every orbital can hold 2 electrons, a P sublevel can hold up to 6 electrons. A D sublevel, okay, and yes, there is clearly a pattern here, okay, a D sublevel has 5 orbitals in it and can hold up to 10 electrons because each orbital has 2 electrons. And an F sublevel has 7 orbitals and can hold 14 electrons. Now, at some point I'll show you a video showing how all these guys fit together in 3-dimensional space, but for now, you just want to be able to kind of fill them in and write a configuration. So let's start with sodium, okay? And let's just follow the pattern on the chart. Since sodium has 11 electrons, right, we're going to just start filling in according to the order here. So it has 11 electrons, so we start off with 1, first energy level, S sublevel. And we're going to put 2 electrons, so put a little 2 there like that. Now once we've done that, right, we can't put any more electrons in there. We move to the next thing, right? So we start filling in the second energy level. Now the first energy level only has an S sublevel. The second one has an S and a P, the third has an SP and a D, and the fourth has an SP, a D, and an F. So right at this point, we have completely filled the first energy level. So then we start working on the second one. Now at this point, we're down to 9 electrons. So the next place we can put them is here. And this is we're going to fill in our second energy level, S sublevel, and we're going to put 2 electrons in there. Then we fill in, okay, the 2p, because that's the next lowest energy. And we're going to put in, we can hold 6 electrons, so we go 2p6. Now at this point, we're down to 1 electron. So where's our next electron go? It goes right here into the 3s. And so we go 3s, but we want 1 electron, so we put 1 there. Now that is the electron configuration for sodium. Now, there are other ways of doing electron configurations or other ways of writing it. So I'm going to get some of those out of the way right now for sodium. And then we'll do some more practice again on the next page. So another type thing is what's called shell configuration. This is what the regents use. And that is basically a listing of how many electrons are in each main energy level. So you can put a big slosh like this and a splosh like that. The shell configuration for sodium would be 2-8-1, meaning 2 electrons in the first energy level, 8 in the second, 1 in the third. Third type of electron configuration, noble gas configuration. Now sodium is right after neon in the periodic table. So this would be the noble gas configuration for sodium. You do Ne bracket. Now neon has 10 electrons, 3s1. Now what is this? This neon represents all this right here, and we just put what's outside after it. Now these electrons here are going to be the valence electrons. On the next slide, okay, I'm going to do some practice with this. I'm going to put the diagram up again, and we're going to do a little more with it. All right, so let's do a few more of these. I'm going to pick a couple of atoms, all right, and it would be very helpful if you had a periodic table for math. You know what, let me put a periodic table in here as well. Okay, so let's do a couple of these, and I put a periodic table up here, and we're going to start talking about how this diagram here is incredibly useful in terms of doing electron configurations. So let's pick something a little bit more difficult. Let's pick an element that's further down here, like let's say, let's do Mn. So Mn is located right over here. Okay, wait, sorry about that. Mn is located right there. Mn is atomic number 25, so this is manganese. And that means as a neutral atom, now again, we should be able, eventually we're going to have to do ions and things like that, but as a neutral atom, this is 25 electrons. Okay, so we can start filling this one in. So we go, okay, we have 25 electrons. We're going to start, now they all start the same way, right? So we start 1s2, right? That's our, now we've wiped out 2 electrons, there we got that. Then we start filling the second energy level, 2s2, 2p6. At this point, we're down to 15 electrons, right? And then the next thing we do is we do 3s, and then we put 2, right? And then we do 3p6, right? Now, you might think that the next thing we're going to do is we're going to do the 3d, because the third energy level has an S, a P, and a D sublevel. But in fact, we don't do that, because it turns out that the 4s sublevel, okay, has less energy than the 3d. And you can see this is called an Aufbau diagram, basically. And what it does, it shows you the relative energy of the orbitals. So you see right here on the diagram, this thing right here has less energy than 3d. So what we're going to do here is we're going to fill in the 4s first. So right now we've used up a total of 18 electrons of our 25. We have 7 electrons left. And the first thing we're going to do is we're going to do 4s2. We put the 2 electrons there. And then after we fill in the 4s, we're going to go back and we're going to fill in the 3d. Now the d sublevel can hold up to 10 electrons. It has 5 orbitals, right? So it's going to be 3d5, like so. And so that is our electron configuration for manganese. Now if we did shell notation for this, right, we would just do, we'd break it up like this. We do 2-8. Now, we count all the ones in the third energy level first. So we're not going to fill in the third energy. We have 2, 6, 8 plus 5. We have 13 in the third energy level, dash 2. And by the way, this is our valence electrons. All right? And if we were going to do our noble gas configuration, we go into our periodic table and we find the noble gas that was the last right there. Now, this is helium, this is neon, this is argon. So we go argon, AR, bracket, bracket, right? And then all this stuff right here, right? So argon is right here. 4s2, 3d5. This, right? Let's do another one. Then we're going to look closely at this periodic table. And yes, this is a relatively long video, so if you need to break it up, go ahead and break it up. All right, let's do another one. Let's do something like complicated and annoying. Let's do tellurium. Tellurium is Te, and Te is all the way down here. That's tellurium. And Te has an electron, has 52 electrons. So Te has 52 electrons, okay? So we start filling it in, right? We start over here first, okay? We go 1s2, 2s2, 2p6, right? So I'm up to here, right? Got that filled in, right? Then I start filling this. I got 3s2, 3p6. Then I do 4s2, 3d10, 4p, and then I go 4p6, and now I better keep track, see what I've done here. I got, this is 10 electrons, 10, that's 20, 30. I've used up 36 electrons so far, so 52 minus 36, right, so that's 40. I've got 16 electrons to go, and I'm up to there, okay, 3d10, 4s2, 4p6, now I go to 5s2, 5s2, 5p6, oh wait, I'm sorry, 4d comes next, 4d10, wait, oh wait, I got 4d10, and the last one is going to be 5p4. So that's our whole electron configuration, right? Let's rewrite it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p4. I'm not going to do the orbital and the noble gas configuration on this. Actually, I'll do the noble gas because it's really easy. See the 4p6? When you get to 4p6 right there, so it's going to be whatever this noble gas is, which is krypton. So it's going to be Kr, okay, and then it's followed by, you know, bracket, bracket, 5s2, 4d10, 5p4. So how are we going to do this? Because you're not going to have this diagram. This diagram is not going to be available to you when you're doing electron configurations, right? So how do we take care of that and not have to deal with that problem? Well, the periodic table makes it easier for us to cheat. As I've been doing this, you may have noticed me like not talking about what's written in here, okay? But if you look at the next slide, we're going to talk about that in detail.